Welcome to the Databricks Skill Builder series. We're glad you're here.
Cool. Thanks, Stephanie. Appreciate it. So my name is Josh Melton. I'm a member of our delivery solutions team. And today I'm going to try something new, make this a little bit more interactive, and hopefully it'll help communicate some of the concepts. So what we're going to talk about today is demand forecasting. And so we have a hands-on example of doing demand forecasting. But before we get to that, a couple of the concepts that I wanted to cover that kind of build into the demand forecasting example are distributing some machine learning processes. So we'll go through a couple of those high-level concepts and then implement them in a demand forecasting example. So what this kind of looks like is we'll have slides and notebooks demos. So this maybe is the part that will be more familiar, right? So we'll talk about what parts of the machine learning lifecycle you can parallelize on Databricks and how HyperOpt and Pandas UDFs come into play. We'll also mention Spark ML and PySpark Pandas. We won't go into detail on those, but just to kind of make everybody aware that those exist and can parallelize other parts of the process that we won't talk about. While we talk about HyperOpt and Pandas UDFs, we'll have a couple of example notebooks. I'll share a link from a repo that will allow you to follow along. And then once we're done talking about HyperOpt and Pandas UDFs, we'll implement those two things in the demand forecasting exercise. So I would anticipate this section taking maybe a little over an hour. And then the demand forecasting exercise, I'll leave some time for you to actually do the kind of fill in the blank exercises. There might be like an awkward silence on the call, but that's okay. I want to give you an opportunity to try this out yourself, and then we'll leave the last 20 minutes or so to actually walk through the solutions. So when we think about parallelizing machine learning on Databricks, if you've seen this slide before, right, we have a bunch of different offerings related to Databricks or related to machine learning on Databricks, I should say. So Delta Lake and ML Flow and Feature Store and all these things are super important concepts. But what we're going to focus on today is model training and tuning and the Databricks runtime and how to leverage the tools that are available to you to do these things faster and at scale. So put a little bit more substance to those concepts, those features and what they actually do from the last slide. First of all, when you do machine learning, obviously you've got to do some data preparation to get your data in a good format and ready to be leveraged in machine learning. Once your data is prepared, you can train a machine learning model. And then once you train a model, you're going to want to fine tune it to make sure the parameters or hyperparameters are appropriately, organized and weighted. And then once you have a fine-tuned version of the model that you've trained, you'll then want to use that model for inference, meaning to make predictions. So when we think about the challenges of doing, this is fairly simple on smaller data sets if you run things locally, Pandas and sklearn and things, but when you get to bigger data sets, it starts to become more challenging, and there's some intricacies to how we scale each of these steps to bigger data. So data preparation with bigger data can dramatically slow down and can even run into out-of-memory errors. So you might have experienced this if you're trying to process a larger data set above, say, 1 million rows with pandas, right? So a couple of the challenges and this is a common theme, right, is slowness as well as potentially out-of-memory errors. Like the problem might literally be intractable if you have too many rows. And then we also have the model training process, right? So similarly, if you have a lot of data, the model training process can slow down or maybe even error out due to limited memory in your computer. And the tuning process, typically, if you train a model, then tuning it will work, right? You won't probably run into out-of-memory errors, but it will slow down drastically. And we'll also talk about how if you don't scale parameter tuning in the right way, not only will it slow down, but it will be less effective. And so we'll talk a little bit more about that when we cover HyperOpt. And then finally, inference can slow down if you don't think about how to scale. And this might literally make your machine learning model kind of redundant or defunct, right? Or not able to solve the problem. If you're thinking about creating machine learning models for a really low latency use case like product recommendation on an e-commerce site, you need that to be super responsive. And if it takes 10 seconds, that's probably too long to even provide any value. So of course, that's a really important step as well. So when we talk about dealing with bigger data and the machine learning lifecycle, we have two aspects, right? We have scale. So how much data can we handle in terms of volume? How much memory do we have on our virtual machine or computer or cluster? And we also have the concept of scaling up versus scaling out. So scaling the computer that we're using to be a larger computer, more memory for one computer, versus scaling out, meaning distributing a workload across many different computers. And so for our purposes, what we're really going to talk about is issues with scale imply that we are running into challenges with memory, like our data set will not fit into memory. And when we think about where this is important, data preparation, I mentioned if you're using pandas in a traditional sense, if it doesn't fit into memory on your computer you're using, you'll run into out of memory errors, or at the very least, it'll be very slow. And we'll talk about how to scale this out using pandas UDFs. We also have model training that can be scaled, and similarly, it can be slow or run into out of memory errors. But we can use Spark to distribute the data, and Spark ML is, this should read ML rather than MLlib. But Spark ML can distribute modeling, and we can also use Pandas UDF for this as well, as we'll see. And the reason this is important is that as models get fed more data, I think this is probably common knowledge, but it's really important to be able to scale to add more data when we train our models, because it improves the accuracy and effectiveness of our models. So, again, it is kind of intuitive or common sense, but the more data we feed the models, the higher the accuracy becomes. And then the other, we talk about scale, the other challenge is speed, or the other solution, I should say, is speed. And so when we have more data, it takes longer to do our processing, our training, our inference. And so, when we're thinking about speed, it's saving time. I gave the e-commerce example, it's certainly one, but it's also, it reduces the amount of time that our developers need to spend developing models. So HyperOpt is a really good example of this. When we're our hyperparameter tuning, which we'll show an example of with HyperOpt. And so the reason this is important is, again, if you're training or tuning a model in sequence, if you have 10 iterations to do, you have to run them sequentially. So it takes 10 times however long it takes to train your model. And so that can be much, much longer of just kind of waiting around for the process to run, as opposed if you could run those 10 processes in parallel, right? So in terms of cost, when we think about hyperparameter tuning, it's really about developer time. It's also important to think about how do we leverage the information from initial training, machine learning model trainings, and future machine learning model trainings. So we'll talk about that a little bit actually right now. So, a couple of traditional ways of doing hyperparameter tuning, I should say, or maybe I should back up and just mention what I mean by hyperparameter tuning. So say you have a boosted tree model, and you have to set some number of how many trees to be used in the model and how deep each tree is. You might not know what the right number to choose is for your problem. And so you want to iterate over those two things to create the best model, the best hyperparameters for your model. Similarly, you might want to try different weights for linear regression or something like that. And so what traditionally people do is a grid search, right? So you have this is some parameter that's like number of trees, right? And this is the depth of the trees. And so you just say, okay, let me try like depth 1 through 10 and number of trees 10 through 20. And then you just try every basically combination of those things and, end up reporting the results. There's also random search. So you lay out the same things and then just take random values rather than the sequential values. But either way, this is not super efficient because you may want to leverage the results of the initial training runs and the future training runs. Like if you see, like in this example, right, say this is accuracy and you realize that it increases up here and this part of the chart that's lower down here. So let's just forget about trying some of these values and focus on fine tuning within these values, right? And if you use a grid search or a random search, you're not really getting that kind of perception. You're not getting that kind of efficiency. You're just going to continue to kind of iterate through all of these points rather than honing in on the most effective point. So this is where HyperOpt comes into play. It's an open source Python library that allows for optimization over very specific search spaces. So you can define a lot of distributions that you want to search over. And what's nice about it is that it can do serial optimization, meaning like sequentially training the model, but it can also do parallel optimization. So as I mentioned, if you want to reduce the amount of time that it takes to get to your fine-tuned model and save developer time, you might want to parallelize the fine-tuning of the model. And it also integrates really nicely with Spark. So it can, again, it parallelizes really well. It's very efficient. And it supports two different things. It supports random search, like we kind of talked about in the past slide, where it randomly selects hyperparameter values. But we also have this adaptive tree of parsons estimators algorithm. And so this is the approach that's going to leverage information from previous training runs to inform future training runs. So tree of parsons is a Bayesian process. It creates a kind of model that basically determines the probability that a hyperparameter will be effective. And this may make more sense as we get into the examples. But as we think about like parallelizing this, right? So first of all, HyperOpt allows us to distribute training our models. So each of these is like a different set of parameters that we fed into our model, and we train the model. And instead of having to do it one by one, we can do 4 at a time in this example. We have 4 workers on our cluster, so we can do 4 at once. What's nice about HyperOpt is it allows us to parallelize this, but it also allows us to say, okay, we've done model trial 1, and let's say the results were pretty bad. Now it's going to say model trial 5. Let's try some hyperparameters that are very different than model trial 1 because it didn't do so well. So now we're leveraging the results from trial 1 to inform trial 5. And then trial 2 finishes up, and that gets a little bit better. So now trial 6 is going to try something closer to trial 2, right? And so on through trial 7 and trial 8 and on down the line, right? It's going to use the information from each of the trials that's completed to inform which parameters it should try in the next trial. So we're simultaneously getting this ability to parallelize and distribute the trials of training our models with different combinations of hyperparameters. We're also using the information gained from the hyperparameters to inform what parameters should be chosen next. And the steps of how this works, I think, are probably better saved for the demo. So don't worry about if this doesn't make total sense right now. But essentially, you prepare your data as normal. You define a function that you're going to try to minimize. So this is some function that trains your model and then returns mean squared error as an example. And basically, HyperOpt is going to try to minimize the mean squared error. You'll also define the search space. So what hyperparameters should you even try? And then you call the fmin operation to put these things together. The fmin operation takes the search space and then takes the objective function and tries all the combinations in the search space to minimize the objective function. So now this is where we'll get into the demo. Are there any questions before I jump into that? All right. So if you'd like to follow along, I've made I'm gonna drop this in the chat. I made this GitHub repo publicly available. And so I've dropped the link in there in the chat. And if you'd like to follow along, and this will be helpful for the interactive exercise later as well, all the content you can follow along by copying that link that I just dropped in the chat and then going to the repos tab, hit add repo, paste that link in there, and then click create repo. It'll take just a few seconds, but you'll get something that looks like this, right? With a folder called demand forecasting hackathon, I think I called it. And the examples that we'll go over first are in the examples folder. Cool. So that should allow you to follow along with this example of running HyperOpt. One quick note, by the way, if you're following along with the example, this is kind of something that has come up with the content from our training team that they've come up with. If you run this setup cell and get an error about the Databricks runtime, what you can do is go to the classroom setup. I'm doing a command click to follow this path, but it's also just available here. If you run into that error for the Databricks runtime, if you go to the include folder and go to common, if you just paste in the runtime that you're using in here, that'll remove that error. So basically, they try to make sure that their demos work for a specific runtime, so folks don't run into issues. I haven't run into anything unless you're using like a super old runtime. But go ahead and paste in your runtime here and try it out. Or I guess you could also, if it recommends a certain runtime and you have access to edit your cluster, you can also edit the cluster Databricks runtime. But I'm just give you that example. 1 moment. So again, let's start with the HyperOpt demo. Feel free to change the DVR that it accepts and then run the setup, and that'll get you the files and different things that you need to run, follow along with the demo. And if you just want to follow along here and watch, that's okay too. So after we run the setup, what we're going to do is just do our normal kind of reading in our data. So we're going to say file path equals the path that was set up in the setup. We're defining the setup, and that links to a Delta file. We're going to say spark.read.format Delta, load up the data from that path, and then store it in a Spark data frame. And then we'll split this out into train, validation, and test data frames. So we'll say Airbnb data frame.random split, and then we'll give 60% to the training, 20% to the test, 20% to the validation. Give it a random seed, and we're good to go. We've got our data prepared. Next, what we're going to do is import some PySpark ML, some Spark ML libraries. Again, I mentioned it. We won't cover it today, but it offers a lot of really efficient approaches for doing machine learning. Whether this is something you're familiar with or not shouldn't be super important. I think the idea is probably pretty universal, where we just define our categorical columns and use a string indexer to kind of convert those to numerics, long hot encode those kinds of things. And we'll take this vector assembler. Again, it just kind of converts all of the numbers into vectors, which allows SparkML to run really efficiently. But here's the important part, I think, to understand is that we have this random forest regressor model. And the random forest regressor is going to be predicting price of our Airbnb data set, right? And then we're going to put this into a pipeline where we have the kind of data preparation, right? The converting the vectors to SparkML, as well as the model, right? The RF, the random forest regressor. And so at the end of the day, the real important part is that we have this regression evaluator here, and it's going to be predicting the label of price, and it's going to save the predictions in the prediction column. So we won't talk about SparkML today. If this is gibberish to you, I think that's okay. I think the important part is that we are defining a model that is a random forest model, and we are calling that in parallel to make predictions about the price, and we're saving those predictions in the prediction column. So here's the part that is important. This is the part we're going to be talking about more in depth. So when we talk about how to do HyperOpt, I mentioned we define an objective function. And that objective function is going to accept parameters, hyperparameters in this case. And those correspond to the hyperparameters of our model. So when we define a random forest regressor model, we want to pass a maximum depth as well as a number of trees. So how many trees are in our random forest, and how deep should those trees be allowed to go? And again, the challenge that we're trying to address is how do we choose these numbers? And so what we're going to do is create this objective function that accepts those parameters as arguments. And then within MLflow, what we're going to do is create this pipeline and pass it the parameters that our function accepted, right? We're going to fit the model with those parameters to our data. We'll make predictions. Using those predictions, we'll get the root mean squared error, and then we'll return the root mean squared error. So now we have a function that accepts parameters, trains a model, and then returns the root mean squared error of the model with those parameters. Next, what we're going to do is import hyperop, and traditionally it's import HP as HP. And with hyperop, what we'll do is define a search space. So for max depth, let's determine, the minimum that we'll try is 2, and the maximum that we'll try is 5. And we don't know which is better, but somewhere in that space, we think max depth is going to be most effective. What we're also going to do is define trees. So somewhere between 10 trees and 100 trees with increments of 1, right? So any full number between 10 and 100 is something that is acceptable to us to try. But again, if you think about like doing a grid search over all of these combinations, 2 through 5 times 10 to 100, right? It's like 3 times 90 or 200, we're talking about like 270 or I don't know if my math's totally on, but hundreds of attempts to solve the problem, when the reality is that a lot of those attempts would probably be wasted because, after a certain amount, if we're trying a max depth of 2 and we see none of it's working, let's just move on and not try max depth of 2 again, right? So again, that's the problem that hyperop is helping us solve more intelligently. So here we're going to import a couple more functions from hyperop. We'll also import NumPy, MLflow, and we are going to turn off MLflow auto logging, although you can leave that on and track all of the models in MLflow. What we'll do here is set the number of evaluations as 4. We'll define this trials object, which is imported from hyperop. And all this is really doing is saying this is basically just a container for all of the attempts, all of the trials. So again, every time we run this objective function, it's going to be storing the results in the trials object. And then we create a variable best hyperparam, which is equal to fmin, which I mentioned earlier. It's another hyperop function. And fmin is what's going to actually minimize our objective function over the search space. So fn equals objective function. Again, that's the function we defined up here. Space equals search space, which again is right up here. Algorithm is TPE.suggest, which is that tree of parsons estimator I mentioned. And you can also pass random if that's your speed, but I'd recommend trying tree of parsons. We'll say max evals is number of evaluations, basically how many times should I try this, and then we can set a random state. So yeah, and then so what's going to happen here is we'll actually see, and I'm not going to do the slide because it takes a moment, but we'll actually see hyperop. We'll see this little progress bar where it sets up some trials. It might run even parallel, and then if you have many trials running, it'll use the information from each trial to inform the next. So we can see we set the number of trials to 4, and it's going to do 4 trials. And throughout the whole thing, it'll track the best loss of each trial. And what's going to happen is, first of all, because we're logging the model here to MLflow, we have all the results of the MLflow experiments. So you can see here, I've run this a couple times. And each of the different combinations of hyperparameters is tracked here. You can see it tried max depth of 4, a number of trees of 83. If you set this to a higher number, it'll probably be more valuable. But the whole idea is that Once we have run those 4 trials, we now have the best hyperparameters from those trials saved to this best hyperparam variable. And now we can use the best hyperparameters to retrain that model, log it to MLflow, and we now have what we have determined to be the best model using the best hyperparameters. And that's HyperOpt in a nutshell. Any questions so far?
No, so far so good.
Sweet. Okay. So the next part that I want to talk about was pandas UDFs. So we mentioned how to distribute hyperparameter tuning. Now we'll talk about distributing some model training. So in this instance, there's a bunch of different approaches to pandas UDFs, and you can actually parallelize all sorts of different pandas operations. But what we'll talk about today is actually doing a grouping by some column. And there's examples on the screen of what that column may be. It may be grouping by a product, as we'll see in the demand forecasting demo. It may be grouping by a stock symbol. It may be grouping by a store or customer. But regardless, what we're doing is potentially training a different model for each one, right? You may need a different prediction model for a different factory or a different product or a different store. And instead of having to iterate through this sequentially, what we're going to do is take each group and run them in parallel. And what this kind of looks like is we have a Spark data frame, right? And the data frame has some column X1, and that, let's say X1 is product, right? We have product A and product B. And we have some pandas code. It works in a single node setting, right? But now we want to distribute it and run it on every single product. So what we can do instead of iterating sequentially through every single product is split our Spark data frame out by product. So in this case, product A and product B. We'll run that pandas function on each subgroup in parallel separately, right? And then in this case, we're training a model. So for each product or each factory or whatever it is we're grouping by, we have separate models. And then we save out the results to a new Spark data frame. So in this case, where the outputs might be, models that got logged to MLflow, and then we'll return the path to each model. That's what we'll see in this example notebook. And in the demand forecasting example, we'll see we can actually make predictions using this as well. There's all sorts of uses of this approach. But the whole idea is that, and I mentioned pandas UDFs as well. It's slightly different, but today we're talking about pandas function APIs. But the whole idea is that either approach allows you to find pandas code that you can then distribute and use in parallel. So it's really convenient for integration, right? You read in data with Spark, but really you don't have to learn Spark at all to run this. You kind of just apply your normal pandas code. So there's a lot of convenience factors about being able to take pandas code and distribute it out across your Spark data frame. It may be an existing model that you want to distribute or scale. It may be a new model and you just don't feel like learning how to implement it in Spark ML. But regardless, it's a convenient way to distribute some functions. This is also helpful. We leverage this approach in a lot of our LLM demos and blog posts that have come out recently. So definitely a good sort of skill to get familiar with. So same deal here. This is using the same repo, but we're using the second notebook in the examples folder. We can run the classroom setup, same kind of thing, where if you run the DVR issue, just go ahead and you can click through and find the common notebook. And within common, if you're running into that issue, you can paste in whatever Databricks runtime you're using right here, and it should work okay. But the setup's going to run, it's going to grab the data and put it in the right place. And essentially what we have is device data in this example. And what we're going to end up doing is predicting a label based on 3 features, which are actually just random. So we'll create our training data set. And we can see we have 100,000 rows that we're creating, and we're just going to create these columns and produce this data frame with record ID, device ID, and then the features, and then the label that will predict. And what we'll do when we run pandas function APIs is that we'll define this schema. And so in this example, we have a column, device ID, and then a data type, integer, number of views, integer, model path, string, mean squared error, float. So this is the schema that we expect to be returned from our pandas function. When we actually implement the pandas function, there's really only two parts that are important. So the function accepts a pandas data frame and then returns the pandas data frame. And if you're not familiar with Python typing, that's all this really is. It's the same as, it's going to produce the exact same thing as this. It's really just a normal function that takes the pandas data frame. But we're basically, this is a promise to say, this is the input is a pandas data frame, and this is the output is a pandas data frame. What happens in between, if it accepts a pandas data frame and returns a pandas data frame, what happens in between really doesn't matter. So in this case, we're defining a function that trains a model for the pandas data frame and then returns the results. So we'll do some parsing of our data. We'll train the model by determining the X and Y, right, the features and the label. We'll create a random forest regressor, this time from sklearn. So again, this is a single node implementation of a random forest regressor. We'll fit that to our data. We'll make predictions. We'll get the mean squared error. And then what we do here is not super important. It's kind of arbitrary, but it's just logging all of the different pieces to MLflow. So with MLflow, we're going to log the model, we'll log the metric, we'll set some tags. We'll also save the artifact URI. And then we'll say return data frame is a pandas data frame that includes the device ID, number of views, artifact URI, and mean squared error, which you'll notice matches the schema up here, right? And then we're just going to return that data frame. So essentially what we're doing, again, is accepting a pandas data frame, training a model, creating pandas data frame that has information about that model, and then returning that pandas data frame. And what we'll do here is now we actually apply the function. So this is defining the function. And now we'll basically just say mlflow.start run, meaning we'll track this information or the experiment in MLflow. We'll say this new model directory data frame is equal to our original data frame with an additional column. And then we'll say group by device ID. So if we think about how this fits into this picture, device ID is kind of like X1, right? We're grouping by some column and then applying this function. That's the function is kind of like this arrow, right? And the function returns some pandas data frame that then gets collected back into Spark. So we say group by device ID, we say apply in pandas, which means we're applying the function after we've grouped by some column. So we apply in pandas the train model function that we defined right here. And then we let it know that the function is going to return a data frame with this schema that we defined up above. And so now what we're going to say is combine data frame. Basically, we join in the results to our original data frame. I think the most clear example is right here in this one cell. So what we're going to do is a very similar approach, but maybe a little bit more straightforward. What we're going to do is define the return schema, which again is just two columns. It's the record ID and the prediction. And what we'll also do is define another function, which again is the same thing as just a regular Python function. But the important bit is that we accept the pandas data frame and return the pandas data frame. And so we will grab the path for a model. We'll define the input columns and then define the data frame that has those input columns. We'll load up the appropriate model to make the prediction. Or if you'll recall, we trained different models for different devices. And then using that model, we'll make a prediction. And then we'll return a pandas data frame with the record ID and the prediction for that record ID. And then we will say our predictions data frame is equal to the original combined data frame. We'll group by device ID. We'll apply this function in pandas, meaning we'll apply the prediction in pandas. We'll return the schema that we promised. And if we display the results, we have predictions per record ID made in parallel. And that is, there's some more content that's good down below, but it's not super relevant. So feel free to explore that on your own time, but I think we'll continue forward on this one. But yeah, just to summarize, right, for the pandas function APIs, we're defining this function that accepts the pandas data frame, it returns the pandas data frame. In between, it does really whatever you want, just pandas stuff, right? And then we define the schema and we basically say group by some column, apply in pandas this function, and then take the schema and promise that that schema is coming as a result. And just to kind of highlight this, right, when you run pandas operations, you don't see the Spark jobs because it's all just running on the driver node. It's actually not running any Spark at all. But here, even though we're running pandas code, and we haven't written any Spark really, other than reading our data, you can see that this was all done in Spark. So you can see like each step of each stage of the different Spark jobs was run, meaning it's going to be super efficient. It's going to be run in parallel. It'll scale out as we talked about, so it'll speed things up and allow you to scale out to more data. Cool. Okay. Two other notes that I wanted to make. We also have, in the Spark community, we have a couple of different approaches for distributing machine learning workloads. Spark ML we saw in the first example. We won't cover it in depth, but it's a really, really efficient way of doing machine learning. And then we also have PySpark pandas. So if you want to do data preparation in pandas instead of having to learn Spark, you can use PySpark pandas to do a lot of operations on what is under the hood of Spark data frame, but you can interact with like a pandas data frame. There are certain limitations to PySpark pandas. So when you run into those limitations, you can use the approach that I just outlined, use pandas UDFs to get around those limitations. So that's why we're not covering that today. Yeah, there's a lot of content out there on Databricks Academy covering both of those topics. All right. So next step for today's demo is to give some time for some interactive workshop exercises. So again, important on this part to have cloned in the repo. We are going to be next looking at the folder number 2 and the hyperparameter tuning section. And here what we're gonna do is run setup again. Before you do that, make sure you click into it and define the database and table that you have permission to. So in this case, I set up the database name as demand planning with my name, and then a cloud storage path that I had access to. Make sure you set this to database. It's not important. Hopefully you're not using this database name already. It'd be a little odd, but make this a database that you're comfortable dropping, because in the next, in the setup cell, or in the setup notebook, I should say, when you are running for this for the first time, you may need to run this with reset_call data to true. And what it's going to do is drop the database and then recreate it and set up all the data. You don't need to do that. Basically what's happening is there's a data generator that goes through and runs a bunch of stuff in pandas to save out data to that database that we'll then use for the rest of the demo. So all that to say, we should run this setup cell and be careful that you're using a database name that you feel comfortable interacting with. So the whole gist of this, I'll kind of turn it over to you all to try this out on your own. But the gist of this is we have an example end-to-end of doing demand forecasting. And so we see that this is all kind of laid out for us, importing a bunch of libraries. And then using the database name from that configuration notebook, we will read in the table at that location. Again, this is the data generated by that setup notebook. When we work through this, there's going to be some code that's already built out. So in this example, we are creating an example SKU data frame that's just limiting our data to one example SKU. We'll convert that to pandas, and then we'll run some pandas functions to essentially just do some forecasting. And then by the end of the notebook, we'll have we'll use hyperops to determine the best hyperparameters to tune this model. And in the next book, the next notebook, what we'll do is do the same thing, but instead of limited to one SKU, we'll use pandas UDFs to distribute it out across the SKU. So we'll group by SKU and then run a pandas function on that. And so what the exercise is if you command F for the two dudes, we have these little ellipses. And then for each one, it'll give you some instructions on how to fill it in. So we can see here, we're choosing a number for the forecast horizon. This is in weeks. So between a year or half a year. So in this case, I'll say 40. And then we see this code is basically splitting it out into historic versus non-historic. So based on the forecast horizon that you define, the code is going to create a column that says is history or is not history. We'll also add, we have code automatically here to add some extra variables. So in this case, we're defining COVID, Christmas, and New Year's. This was like a really pertinent example when folks couldn't predict demand due to drastic changes after COVID, right? So this is an example of a way to mitigate some of those risks. So that code is already determined, but our next to do, already did that one. So to do number 2, we go to, this is the objective function, right? So we have this function, it accepts some parameters. And then when we create this function, what we're going to do is fit the model to our data using those hyperparameters and then return the results. So feel free to dig in a little bit deeper and walk through each line by line. But again, just to kind of get you started on the solution, we can go to the ellipses and we'll say model1.fit. And if you get stuck, there's helper guides right here above the cell where you have to fill this in. And we also have the solutions in the repo. So if you're if you're really stuck, don't spend too much time on it. Just take it the solution and then move it. So I'll give folks maybe 30 minutes to fill these in on your own, and we'll meet back after that to walk through the solutions. All right. So our 30-minute timer is up. I'll just quickly go through some of the solutions and talk about why things are set up the way they are. So if we go to folder 3, we already saw this bit earlier, so we're just reading in the data that we ran in the setup cell. We're collecting data for one SKU, creating the forecast horizon of 40, and then splitting out the data into historical versus non-historical. So we can see this is the SKU that we're working with. We also have a bit where we're doing pandas transformations on that data frame that has one SKU to add the days, like a column true or false for is COVID, is Christmas, is New Year. And then we're going to fit a model. We're using SeriMax. You could plug in pretty much any model here. That's just a time series analysis model, and we'll fit the model to our data with a few different parameters. We'll make predictions, and here we're using with and without those extra sort of time variables that we had. And we also plot the results, so you can see if we're using those kinds of time-based variables, those predictions are in the green as opposed to the blue without, and then black is real ground truth. So we have some pretty reasonable predictions of our demand. And so, we run this on one SKU with kind of arbitrarily determined hyperparameters. So next, of course, we're going to apply those hyperopt principles that we learned about to determine what are the best parameters. Our Serimax model takes P, D, and Q as parameters. And so in this cell, what we're doing is creating our objective function that accepts hyperopt parameters, creates a model with those parameters, fits the model to our data, and then makes predictions. And then using those predictions returns the loss. We'll next determine the search space. So again, this is using hyperopt. We'll define a uniform space for each of these variables from 0 to 4 by 1, 0 to 2 by 1, and 0 to 4 by 1. And then within ML flow, so we track each result within ML flow, we'll store the maximum, like the best hyperparameters as returned by the fmin function. And we're passing that function, the evaluate model function that we defined up above that returns the loss. We'll also pass it the search space defined. We'll let it know to use tree of Parsons estimators, and we'll say evaluate a maximum of 10 trials. We'll pass it a Spark trials object, initialize some random state. And you can set verbose to false to not get all of the progress bars printed out. But at the end of the day, the important bit is that we've logged all of these runs to ML flow, and then we can see the best run or the parameters for the best run in this argmin variable. And then moving forward, we can use these three. They're printed out here. D is 2, P is 1, Q is 2. And so we've now determined that these are the best hyperparameters for our model. So now that we've done that for one SKU, what we'll do is run the setup to point our notebooks to the right data and import all the packages, read in the table, and set the forecast horizon just like before. But what we're going to do is now take those pandas operations that we're running in single node and then apply them in parallel. So this should look familiar from the original or the initial trainings, where we have a function that takes a pandas data frame and returns a pandas data frame. It does some pandas things, right? This is the same operations before to create columns for COVID, Christmas, and New Year's. And it returns the data frame, the pandas data frame with all of those things added. We'll also create a function that splits, trains, and scores our data set and define the schema that we expect to get back from the results of those functions. And then we're kind of lined up to do the same thing as we did in those examples. So we'll take our original demand data frame, we'll group by the product column, we'll apply the function up here, the pandas function, to each sort of sub data frame, each product's pandas data frame. We'll let it know this is the schema that we'd expect, and then we'll display the results. And so we can see we have, for many different SKUs, the demand predicted, and we also have some of these time-based variables outlined here. Or this is not the predicted demand, I should say, this is the actual demand. And again, this is what we're doing at a high level. We have this original data frame, we're grouping by the SKU, and we're using apply in pandas to apply that function across each sort of sub data frame, each SKU's data frame. And then what we'll do is use the same technique to build, tune, and score a model for each SKU. So this was kind of the big cell where we define this big function. And again, it's going to be a pandas function that accepts a pandas data frame and returns a pandas data frame. We'll sort the data to make sure it's in order because it's time-based data. We will define the product and SKU and the extra time-based variables. We'll define a function for evaluating the model based on some hyperparameters, and then do the same thing as in the previous notebook, right? We'll get the hyperparameters, we'll train the model, or define the model, I should say, that accepts those hyperparameters, fit the model to the data, make predictions using the fit model, and then return the loss. And then we'll also define a search space, and then we'll find the best hyperparameters for that particular model. And then we'll actually make return the model, or I should say we'll define the model and then make predictions using the model and return the results. So here we actually combine both approaches, where we have a pandas UDF, where within the pandas UDF, we iterate over some search space and find the best hyperparameters within the pandas UDF, and then return the results and make predictions with the model following the best hyperparameters. We'll define the output schema that we expect to have after making those predictions. And here's where we actually get our forecasted demand across all of our products as tuned. And each model is different and tuned per product. So as we think about the demand for different products being impacted differently by New Year's or Christmas or COVID, the hyperparameters might be very different for each product. So in this case, we are parallelizing by product and SKU. So we'll group by product SKU, we'll build, tune, and score a model for each product and SKU, and then run those in parallel. And here we can see the results. And again, running over thousands of records in a couple dozen seconds, and tuning a bunch of different models and all of these things, and logging them to MLflow is pretty powerful. And then if we want to forecast or save the forecasts out to Delta, we can do so here. So end to end, we've gone from training a single node model to training many models in parallel and fine tuning the hyperparameters for each of those models. All right. Thanks everybody for joining. I appreciate it. I'm gonna go ahead and stop the recording.